Good morning, students. Today we are going to discuss about lacings and battens which are used in a built-up compression member. So till now we have been discussing about how to find the compressive strength of a member and also how to design a compression member. Okay, now we are going to discuss about built-up compression member and the members which are used to make a built-up compression member, and that is lacings and battens. Okay. Suppose for the compression member the magnitude of the load is very high, such that a simple section cannot take up the whole load. In such a case, we will have to combine two or more sections to carry that load, and such a section is known as a built-up compression member. For example, if we are connecting two channel sections, this is a top view of that column. We are connecting two channel sections back to back, and it is connected by using plates on either side. Okay, this is the top view of that built-up section. Similarly, if you are connecting four angle sections and it is connected either in both sides, or it can be connected in four sides by using plates, this is also a built-up section. Okay, just understand these are the top view of that section. Okay, now we can see a front view. Suppose we'll take the first, this one, channel section, and from the front we can see the channel sections like this. We can see the flange portion of the channel of both of them, and these are to be connected in such a way that the column section will be acting as a single member, and it is done by using lacings and battens. Okay, battens are these horizontal members which are used to connect the main members. This is a batten. Okay, similarly, another type of member which is used to connect members are, it may be inclined like this, and these are known as lacings. Okay, the built-up sections has to be tied in such a way that the whole section will act as a group. So we need to tie the members using lacings or battens. Okay, in this figure you can see lacings. First we are discussing about lacings. So you can see that the two eye sections here, the top view is given like this. Two eye sections are connected on either side by using plates. Okay, and these members are known as lacings. So generally lacings are preferred in case of eccentric loads, and lacings are the most commonly used type of most commonly used in case of a build type member. And as a lacings we can use flat bars, which is most commonly used, and also angle sections and channel sections can also be used as lacings. Next is battens. Battens are the horizontal members, as we have seen previously. You can see in the figure. Commonly plates are used as battens, and it is generally used for axially loaded columns, and also where the components are not too far apart. The main members or the components are not too far apart. In such a case, battens are used. Okay, so in this class we are going to discuss more about lacings, the design of lacings, the main specifications that we have to consider while designing a laced column. Okay, this we can see in section clause 7.6 of IS 800. Laced columns, here all the important specifications are given. and this is a figure of laced column, and we can give laced column in either ways. This is a single lacing system, and this is a double lacing system. Okay, here also you can see these are single lacing system and these are double laced system. Okay, and the main failure modes of a laced column are the buckling of the built-up section as a whole, buckling of the main components, distortion of the section, and failure of the latticed members, or those lacing members, failure of the lacing members. These are the four types of failure modes. So you can see the figure. Next we are discussing about the main features or the main design requirements for the lacings. Okay, general requirements, you can see it in clause 7.6.1 in IS 800 2007. Okay, the first point is the members comprising two main components laced and tied should have a radius of gyration about the axis perpendicular to the plane of lacing, not less than the radius of gyration about the axis parallel to the plane of lacing. That you can see here, XX is the plane parallel to lacing system and YY is the plane perpendicular to the lacing system. And the condition is, in a laced system always Ry, that is the radius of gyration perpendicular to the lacing system, will be greater than the radius of gyration in the axis parallel to the lacing system. Okay, Ry will always be greater than Rz. Okay, so the more critical section will be the plane parallel to the lacing system. The next point is given as the lacing should be uniform throughout. While giving the lacing system in a column member, it should be uniform throughout in the dimensions, length of the lacing, inclinations given, all should be uniform throughout. This is done to so that the stress distribution is uniform throughout the member. Okay. Okay, now the important design specifications of a laced column. First one is the most important one. The lacings should be proportioned, or lacings should be designed to resist the transverse shear at any point. Transverse shear at any point, that is the shear acting perpendicular to the load direction. In a column, the load direction will be like this, and in a built-up column, there will be transverse shear, and the lacing should be designed to resist the transverse shear at any point, and we will get the transverse shear value Vt is equal to 2.5% of the axial force in that column. Okay, suppose P is the axial load in that column, then our lacing should be designed to resist a transverse shear V, which is taken as equal to 2.5% of the load. Okay, and it shall be considered as divided equally among all the transverse lacings, and this transverse shear is equally divided among all the transverse lacing. Okay, then the members carrying calculated bending stress due to eccentricity of loading, applied end moments, and lateral loadings. The lacing shall be proportioned to resist the shear due to bending in addition to that specified in close 7.6.6.1. Okay, we'll leave it. The next important thing is the force on each bar. In each bar, in a laced member, in each bar, what is the force acting? For a single laced system, we can see that this is a laced bar, and you can find the direction of force, compression force acting in that laced bar F, and the lacing is inclined at an angle theta. So the transverse shear, the transverse shear acting in that bar is V by N, where in that particular plane, suppose there are n number of lacings in a single laced system. In that plane there will be two bars. Okay, so here resolving the force in horizontal direction, we will get V by N is equal to F sin theta. V by N equal to F sin theta, where N is the number of transverse system in the parallel planes. So in a single laced system there will be two lacing bars on either side of the column, so N will be equal to 2, whereas for a double lacing system N will be equal to 4. Suppose see, this is a laced column. In this side one lacing system, and on the other side also you can find on the here, let's see this case. In this plane, this is face A. Face A has one lacing bar, and similarly on the other side of the column you can see another lacing bar. So in this plane there are two lacing bars. Similarly in a double lacing system, in this particular plane there are two lacing bars on either side of the column, right? In this side of the column there are two lacing bars. Similarly on the other side of the column there are two lacing bars. Thus N is equal to 4 in a double lacing system, and N is equal to 2 in a single lacing system. Okay, so force on each bar is equal to F is equal to V by N sin theta. By rearranging the equation, we will get the force on each bar F. So for a single lacing system, N is equal to 2, so the force on the lacing bar F is equal to V by 2 sin theta, and for a double lacing system, force on each bar is equal to V by 4 sin theta. So this is for checking the compressive stress and tensile stress. The compressive stress on each lacing bar, if the lacing bars are flat bars or simple rectangular bars, we can use this. Compressive stress on each bar F, if we get the force on each bar, then we can find the compressive stress on each bar F by B into T, and it should be less than sigma AC, allowable compressive stress. Okay, this allowable compressive stress value we can find from the steel code IS 800, and it will be 0.6 times FCD value, design compressive stress value. Allowable compressive stress equal to 0.6 times FCD value. And similarly for tensile stress in each bar, F by B minus D into T, it should be less than the allowable tensile stress. The value of allowable tensile stress is 0.6 times Fy. This also we can find from the IS 800. Okay. So now next point is slenderness ratio. Slenderness ratio of a laced column should not be greater than 145. This is important. Slenderness ratio of the laced column should not be of the lacings. Slenderness ratio of the lacings should not be greater than 145. Where L, here the L is the length of the lacing member. Length of the lacing bar. K is the coefficient to be given. R is the radius of gyration. Okay. So the coefficient value will depend upon the type of connection. So here for a single lacing system, if it is bolted or riveted, then the effective length is equal to length of that lacing bar itself. On the other hand, if it is a double lacing system and the ends are connected by riveted or bolted, then effective length is equal to 0.7 times the length of the lacing bar. And if the lacings are welded, then also effective length is equal to 0.7 times length of the lacing. So we have to find section such that the slenderness ratio will not be greater than 145. Okay, if it is greater than 145, we have to change the section. So commonly we are using flat bars as lacing members. So in for lacing members, slenderness ratio lambda is equal to Le by R. Substituting the value of radius of gyration for a flat member means rectangle of width B and thickness T. In such a case, the slenderness ratio lambda will reduce it to Le root 12 by T. We don't have to find the radius of gyration by equation. We can get the direct slenderness ratio equation for a lacing bar, rectangular bar. Le in the root 12 by T, and it should be less than 145. Okay, so for checking the slenderness ratio, we can directly use this equation. Le root 12 by T. So we have to substitute the effective length value and thickness of the lacing bar, and we can find the slenderness ratio of lacing bar. So next is width of the lacing bar. Width of the lacing bar should be greater than 3 times nominal diameter of bolts or rivets. And then thickness of lacing bar. Thickness of the lacing bar should be greater than Le by 40, effective length by 40 for a single lacing system. Thickness should be greater than Le by 40 for single lacing system, and it should be greater than effective length by 60 for a double lacing system. Okay. Now the angle of inclination of the lacing should be between 40 degrees and 70 degrees. Should be more than 40 degrees and less than 70 degrees. Angle of lacing means the angle made like this. This is the angle of inclination of lacing. It should be between 40 and 70. Now the spacing of lacings. Spacing of lacing means this is known as the spacing of lacings. The spacing of lacing should satisfy this condition. That is, spacing of the lacing divided by R minimum of component member. R minimum of component member should be less than or equal to 50 or less than or equal to 0.7 times lambda of the whole column section. Okay. Okay. So we can find R minimum of whole section as LE by R minimum, effective length of R minimum. And the smaller value is to be taken while considering the condition. Okay, now we will be doing a problem. The question is, design a built-up column consisting of two channel sections placed back to back with a clear spacing of 250 mm between them. The column carries an axial load of 1000 kN and is having an effective height of 6 meter. Design the lacing for the column. So given that two channel sections are to be connected back to back and the clear spacing between the two channel sections is 250 mm and the axial load carried is 1000 kN and the effective height of the column is 6 meter. Design the lacing for the column. So we know that the direction parallel to the lacing system will be Z and the direction perpendicular to the lacing system will be YY, and then after giving the lacings it should be such that the radius of gyration of Z will be less than radius of gyration along Y direction. So we have to design in such a way. The lacing should be designed in such a way that RZ is less than RY. Okay. So write the given things: axial load 1000 kN, permissible compressive stress. Permissible compressive stress, we are assuming permissible compressive stress is 0.5 times Fy. Okay, that is 125 Newton per mm square. And by using the equation that we know that the compressive strength P is equal to A effective area into stress permissible like design compressive stress FCD, but here we are assuming permissible compressive stress as 125 and the PS, the load, factored load given, such that we have to find the area. We have to find an area which can satisfy the factored load and the stress developed. So here area is equal to P by allowable compressive stress. So 1000 kilonewton is converted into 1000 Newton by 125 Newton per mm square. So we will get area required as 8000 millimeter square. Okay. So we have to design a double channel section, two channel sections back to back. So this area is for two channel sections. Area required 8000 mm square is for two channel sections. So we have to find a channel section, two channel sections, and whose total area will be more than 8000. So check on SP6 and we can find a section whose area is almost half of 8000 or nearby 4000, and we found that ISLC 300 is having an area of 4211. Here it is given in centimeter square, that is 42.11 centimeter square. Okay, so this area is okay for us, and give two ISLC section. ISLC means Indian Standard Lightweight Channels. Just note down, just see that line, we can find all the important characteristics of that channel section. And first we are trying this section. We have to try this section ISLC 300, and the total area will be equal to for 8422 mm square. And R set value, here we require R set value for designing the lacing system. R set value is equal to 119.8 mm. As you can see in that SP6, you will find that for ISLC 300, R set value is 119.8 mm and RYY is 28.7 mm. So actually from this table we can find that RY is less and R set is more. But we have to take R set. We have to take R set value, because while designing a lacing system, the R set should be less than RY. This is important. So we are taking R set value equal to 119.8 and take lambda whole is equal to effective length by R set equal to 50.083. And listen, here we know that one condition is there. The slenderness ratio, we have to convert effective slenderness ratio of laced column is equal to 1.05 times slenderness ratio of that column. So 1.05 times lambda. So actually in this problem we have not done that, but actually we have to do that. Lambda is equal to 1.05 times lambda for a laced column. So find lambda E, and for a channel section the buckling class is C, and FCD value is 183, which we get from table 9C. Okay, this is actually a built up section, so we have to find the compressive stress FCD value from 9C. So FCD is equal to 183. Actually if you are doing in lambda effective value, the value will be different. It will be more than this. FCD value will be more, and PD value, compressive strength value will be also be more, and that compressive strength should be greater than the given factored load. Okay, this is the compressive strength of the column. So this compressive strength should be more than the given axial load. So adopt the section. Now we will adopt the now we will design the lacings. Assuming 16 mm bolts, then minimum width of the lacing bar will be equal to 3 times the diameter of bolts, that is 48 mm, and it should be more than that. The minimum lacing minimum width is 48, so we can give more than that. The given width is 50 mm. Angle of inclination is 45 degree. Today we can take in between 40 and 70, so the angle is taken as 45 degrees. Now thickness of lacing bar, we are taking a single lacing system, we are taking a double lacing system, so effective length is LE and thickness should be greater than LE by 60. So we have to find the effective length of the lacing bar. From the figure, if you place the lacing in 45 degrees, we can see that 250 is the clear spacing between the two columns, and assuming the lacing to be placed at 60 mm from this end, so from either side 60 plus 60 plus 250 center to clear spacing, we will get 370 mm as the width, not width, actually it is the horizontal distance. And since it is inclined at 40 degree, this is 370, this distance, horizontal distance is 370. Since it is inclined at 45 degree, this side will also be 370. Okay, so we can find the length of the lacing system as, this is the length of the lacing system, L is equal to root of 370 square plus 370 square equal to 370 into root 2. That is the length of the lacing member. Okay, so effective length for a double lacing system, effective length is equal to 0.7 times length of the member. So we got the answer. Now thickness of lacing bar should be more than minimum thickness should be effective length by 60. Okay, so we will get it as 6.10 mm thickness, that is the minimum thickness. So we will provide more than that. We will provide 10 mm thickness. Now spacing of the lacing system, we know the condition, spacing of the lacing by R minimum of the component member, it should be less than or equal to 50 or less than or equal to 0.7 times LE by lambda whole, 0.7 times lambda whole, or LE by R minimum of whole section. Okay, so here the difference is R minimum of component member means, for the channel section we already know that RY value and R set value, RY value is 28.7 and R set value is already found 119.8. so for this R minimum of component member, we have to take the actual lower value. Actual lower value is RY 28.7. Here is the difference. Spacing we have given as 370. Spacing of the lacing is 370. Right. Spacing is the vertical distance between lacing ends. This is the spacing, that is 370. We already know. So 370 by R minimum of component member, actual R minimum 28.7, and it should be less, it is 12.89, it should be less than or equal to 50 or less than or equal to 0.7 times lambda whole. So it is 35.05. So in this the smaller value is 35.05 and our spacing by R minimum of component member is 12.89, which is less than 35.05. So that is condition is okay, spacing is okay here. Now check for slenderness ratio. We know that the lacing rectangular bar is used, so KL by R for flat bar should be less than or equal to 40.5 for 145, and for a lacing bar we have the equation LE root 12 by T. We know LE value, T value is 10. Substituting we will get 126.8, which is less than 145 mm, so it is okay. If it is not okay means then we have to change the thickness of the lacing bar. Now check for bars, check the bars for lacing in compression. We have to check for the strength. Now we are checking for the strength. Okay, we already know that the transverse shear or shear force in the lacing bars V is equal to 25 kilonewton, and the force on each bar, the force acting on each bar F, this is a double lacing system, so force on each bar is equal to V by 4 sin theta. Theta is 45 degree. We will get force on each lacing bar as 8.84 kilonewton in a particular plane. Okay, now we have to check for compressive strength of the lacing bar. For the lacing bar, lambda is equal to 127. Today we got 126 point something, we are taking it as 127, and for that lambda for flat angle buckling glass is C, and will from the table 9C we will find FCD value, which is equal to 77.15. Therefore the compressive strength of the lacing bar is PD is equal to 38.6 kilonewton, and it is greater than the force on the lacing bar 8.84. The compressive strength is more than the force on the lacing bar, so it is safe. Now we'll check for the flat bars in tension. In tension we'll find the TDG and TDN, section yielding and gross section in tensile strength in yielding and tensile strength in rupture. For yielding, AGFY by gamma m naught. AG we have width, we have taken the width of the lacing bar as 50 mm, and thickness also we have found out 10 mm. So AG Fy value by gamma m naught is 113.4. It is greater than 8.84. So in tension yielding is okay. Similarly in tension in rupture, 0.9 AN. AN we have taken as width minus D naught into thickness. Okay, so considering one bolt hole, we got the answer as 94.46 kilonewton, and it is also greater than the force on the member. So the flat bars are found to be safe in tension. Okay, so this is the design of lacings.